So far we looked at what is magnetocrystalline energy dependent on. So it was spin orbit coupling, and we briefly looked what is spin orbit coupling. But now we wanted to see how we can experimentally see it. So magnetocrystalline energy is usually just the work done, so energy which is stored as a work done to magnetize a material under an external field. So you apply an external field and it gets magnetized, and how much you have to do work for it is going to be in the end magnetocrystalline energy. So if this energy is very large, you have to do more work to magnetize, and if this energy is small, you have to do less work. We have seen previously an example of cobalt. So here you can see that cobalt, this magnetocrystalline energy from this equation is just area under the curve of an MH loop. So if you measure magnetization as function of field, the area under the curve will give you magnetocrystalline energy, ignoring how the domains are formed and all other things. If we just consider one axis is hard and one axis is soft, the curve will just give you information about that. So you can see that for this cobalt, you have measured magnetization along two axes. One is along C. So you can see that the black color which is area under this curve is very small, so it's an easy axis. However, if you want to magnetize along the perpendicular to the C axis within the basal plane, you have to apply much larger fields, and then area under the curve is really large, so magnetocrystalline energy in this direction is also large, so it's a hard direction. So looking back to this equation again, we can approximate it to an anisotropy constant, which can tell us about the how much anisotropy is present in our system. So for this one, we can just approximate this work done to saturation magnetization multiplied by anisotropy field, where an anisotropy field here is just the field required to saturate along the hard axis. So in this case, it will be field required to saturate magnetization perpendicular to the C axis for cobalt. And then this difference of the work done can be approximated to the uniaxial anisotropy constant. So this is also a type of magnetocrystalline energy, but uniaxial anisotropy is also magnetocrystalline anisotropy, but for specific crystal structures, which we will see in a minute. But okay, this is a magnetocrystalline anisotropy constant, which we are going to estimate for this structure cobalt. So by considering the anisotropy field, so here in the graph we can see that it will saturate somewhere ahead in this curve, and we can write it as 5.6 10 to the power 5 amps per meter, and which will be equal to 560 kiloamps per meter. So then saturation magnetization for cobalt is around 1.4 10 to the power 6 amps per meter. So in this way, by putting all these values, we can find that the anisotropy constant is this value. And now we will see in a while that we can also estimate this anisotropy constant theoretically. And for the first order approximation, if you only consider the first anisotropy constant, which is Ku1, there are higher order Ku2 and so on. So the first one, the value is very close to what you have estimated. So in principle, you can ignore higher order terms, and first term can tell quite good about the anisotropy in the system. So in this way, we can actually find out what type of anisotropy constants are there, and depending on if these anisotropy constants are positive or negative, large or small, one can really understand how the magnetization will depend on different crystallographic directions. So the anisotropy constant which we have shown can be estimated from these galaxies is actually a very rough estimate. To really find out the proper contributions of anisotropy, one has to consider the energy density, magnetocrystalline energy density, and write in terms of anisotropic constants for different crystalline structures. For that, we can actually show the magnetization N in Cartesian coordinates with directional cosines like this, shown the relation here. Or you can show the magnetization in the spherical coordinates with theta and phi polar and azimuthal angles. So in this way, one can actually start and show the free energy density. One important point here is that for the directional cosines, one has to consider that the square of these directional cosines is equal to 1, which means that the magnetization unit vector is uniform over the whole sum. The most convenient way to express the magnetocrystalline energy density is in terms of spherical harmonics, which is represented here. So here I denote the magnetocrystalline energy density as G crystalline, but in principle you can give any symbol to this. So here the right side contains the expression for spherical harmonics, where this k, small k, is actually anisotropy coefficient. So for second order anisotropy, you will have y2 and term, meaning that the spherical anisotropy coefficients are going to be 5, because you have to give n a value from minus L to L, so you will get 5 coefficients. So in this way, usually it's more convenient for theoretically to put energy density in this form. However, traditionally we do not express energy density like this, but in the anisotropic constants instead. Here Hn is the projection of the magnetic field in the direction of magnetization, and M is the unit vector of magnetization. And N is taken here, even it has to do with that the energy density should stay same under the time reversal symmetry, how it's defined here. So by replacing n to minus n, it should stay the same. An alternative way to represent the energy density is in terms of directional cosines, and this is done by showing the anisotropy energy in successive powers of directional cosines alpha 1, alpha 2, alpha 3, and here is the expression, and with this directional cosines you will get some constants, B0, Bi, J, and so on, and these constants are later on related to anisotropy constants. So if we look to the relationship between crystal structure as well as anisotropy constants, so more we go down, the system becomes more and more ordered, and that much less anisotropy constants we need. So going downwards, so for right limit we will need more anisotropy coefficients and more anisotropy constants, and if we go down towards the orthogonal and cubic, we will need less anisotropy constants as the system is getting more and more ordered. As an example, for cubic or tetragonal systems, usually we can mostly describe them with just second order anisotropy contribution, anisotropy constants. So if we talk about spherical harmonics, you will get For second order, you will get 5 anisotropy constants. So if you go now less and less ordered system, you may need to consider higher order. As we said that we have to take care of time reversal symmetry, so we only consider odd power, we only consider even powers of spherical harmonics. So for considering higher order, we consider second order, fourth order, sixth order. So if you have to consider fourth order, you will get 14 anisotropy constants, and if you go to sixth order, you will get 27 anisotropy constants. So more and more system get towards less symmetry, the more anisotropy constants you will need.